This is part two of the kinetics lecture where we talk about complex reactions. And specifically, what it really means for us to be talking about complex reactions are those reactions in which you have two or more reactants being mixed with each other, leading to formation of products. Reactions like the combustion of acetylene, the chlorination of methane, oxidation of iron, single displacement reactions, or even acid-base reactions, they do have multiple reagents present, and so they're a little bit more complex than the situations we investigated in lecture 3. And in the past, I've shown you that when you go from reactant to products, you have an activation energy that you need to surmount in order to get to the product side of the reaction. But when you have reactions in which there are more than two reactants present, the reality is that you don't just have a simple activation hill. In reality, what ends up happening is that there's a multitude of steps that happen sequentially. And for instance, in this graph here, you can see the reaction in which this carbon-chlorine bond starts breaking up, leading to an activation energy. And when that bond finally breaks apart, it forms a cation known as a carbocation. But this thing here is not actually a stable product. It's what we call an intermediate, because as soon as it gets produced, it starts reacting away with some other reactant present in solution to give you ultimately the final product. And so what you can see right here is that in the energy profile of this reaction, there's a total of two activation energy barriers. But the first one happens to be the tallest one, or the one with the most energy value associated with it. So by default, the first step in this reaction is what we will call the slow step of the reaction, and it will define how long it takes for the reaction to complete. But as you can see, it's actually now present in multitudes, or in a multitude of steps. So we're going to address that issue towards the end of the lecture. But what I want to show you right now, before we get into the idea of looking at elementary steps, is to determine the orders of reaction. So you may recall that the rate law of a reaction is given by the negative rate constant times the concentration raised to some power. And that power could be 0, first, or second in terms of the order. And this was simply if we had just one reactant. But if we do have more than one reactant present, we actually have to determine the order for every reactant that the overall reaction has present. Alright, so we're going to basically concentrate on this particular task. And there's two ways to do this. I'm going to show you the first way, which involves looking at initial rates of reaction. So you could actually look at the change in concentration over time, and specifically narrow down on that rate at the very beginning of the reaction. And so you can actually collect initial rate data based on initial concentrations of both reactants. So for the reaction right here, which is the chlorination of chloroform, the chlorination of chloromethane, you have different concentrations of both reactants, and that also lead to different initial rates of the reaction. So the idea right here is that the rate constant can be determined, and also the orders of the reaction can be determined by using the generic rate law of this reaction, which is simply going to be negative K, which is the rate constant, times the concentration of the first reactant raised to some power, we can call this power X, and times the concentration of the second reactant raised to some other power, a power of Y. Now we cannot say that the powers are 1 and 3, which are the balancing coefficients, because the fact that we have multiple reactants present means that we're going to have multiple elementary steps happening leading up to the formation of the products. So we don't know exactly which one of those steps is going to be the slow step. So we have to find out with the experimental data here what the values of X and Y are going to be. Alright, so the way you do this is to look for rows of data in which the concentration of one of the reactants is constant. And if you look specifically at this table, you'll notice that for rows 1 and 2, the concentration of Cl2 is constant. So if you take the data for row 1 and row 2, you could actually divide the rate of row 1 by the rate of row 2. And because the rate law is still negative K times the concentration of CH3Cl to the X power times the concentration of Cl2 to the Y power, that will be true for both numerator and denominator. But what's going to differ is that the concentrations are going to change. Now, because the Cl2 concentration is the same in rows 1 and 2, what that means is that not only are the K constants going to cancel out when you divide the two rate laws from each other, but you will also cancel out the value of the chlorine. And also another thing to point out is that because you have the concentration of CH3Cl raised to the x power on both top and bottom portions of the equation, you can simply factor out the exponent x the same way you can factor out the exponent y for the second reactant. So plugging in the values, what you're going to see is that you have 0.05 divided by 0.05 for the concentration of Cl. We've noticed that already because we selected the two rows such that we can cancel out the component associated with Cl2, right? So this whole thing is cancels out. And so what you end up with is simply the rate of the first row divided by the rate of the second row, which now is solely going to equal the concentration of CH3Cl in the first row divided by the concentration of CH3Cl in the second row. All of that raised to the x power. So if you actually plug that into your calculators, you're going to find out that the first fraction on the left side equals 0.483, and the fraction on the right side of the equation equals actually 0.5. That should be 0.5, not 0.05. So 0.5 raised to the x power. Now, in some situations, this may seem, might actually be obvious as to what it is that you're dealing with. But if it is not obvious, the thing that you need to do is take the logarithm of both sides of the equation. So you take the logarithm of 0.483, take the logarithm of 0.5 to the x power, and one of the rules of logarithms that helps you out big time here is that exponents inside logarithms can be brought outside as multiples, right? So that 0.5 to the x power can be now rewritten as x times the log of 0.5. And so the final thing that happens here is that you can divide both sides by the log of 0.5. And now you have log of 0.483 divided by log of 0.5, which equals x. And if you plug all of that in the calculator, you're going to find out that this ultimately equals 1, telling you that the order of CH3Cl is actually first order. Alright, now with that information that we just gathered in this example, now that we know that x equals 1, we set out to look out for the value of y. And if possible, you may try to select two rows for which the concentration of CH3Cl is constant. And it looks like rows 2 and 3 will do the trick, but because we already have the value of the exponent for x, we can actually use whichever row we want, whichever two rows we want to make this happen. And I mean, I'm not out of a way of showing you, to the full extent of how to solve this problem. I'm going to pick rows 3 and 4. So for rows 3 and 4, we have 0.041 for the initial rate and 0.115 for the initial rate of the fourth row. So now the concentrations of CHCl are different in both of those rows, the same way that the concentrations of Cl2 are also different. But now the difference is that we do know the value of the exponent for CH3Cl. So if we go ahead and carry out the divisions, 0.041 divided by 0.115, and press enter in your calculator, you're going to get a value. If you divide 0.1 by 0.2, you're going to get 0.5 raised to the first power. And if you divide 0.1 by 0.2, you'll once again get 0.5 raised to the value of y. Right? So this is basically what we get by carrying out those divisions. Then what we basically do is we solve for 0.5 to the value of y, so divide by 0.5 in other words. That turns the 0.357 into 0.713. And now we take the log of both sides. So we have log of 0.713, log of 0.5 to the power of y. And at this point, we bring the y as a factor in front of the log. So finally, we divide both sides by the log of 0.5. And if we carry the calculation, the division of log of 0.713, all divided by the log of 0.5, we're going to find out that the exponent in association with Cl2 is actually 0.5. So this is a fractional exponent, and this can actually happen. So if you write the rate law for this reaction, you will have rate equals negative K times the concentration of CH3Cl to the first power times the concentration of Cl2 to the 0.5 power. And in the future, if you're asked to solve for the full rate law, including the value of K, then you have to basically pick any value, any row, plug in the concentrations of CH3Cl, the concentration of Cl2, and the value of the initial rate, and you have to solve for K at that point. All right, now I'm going to stop this right now, and we're going to do another example in the next video. So see you then.